Well, so lastly we discussed about different parameters like Y parameters, Z parameters, scattering parameters, ABCD parameters, and found relationships among them. And also we discussed some special scenario like lossless network, reciprocal network, and then how the scattering matrix it looks like. And also we discussed when there is a change in reference plane, then what is the effect on the scattering matrix individual element. After that, we discussed about signal flow graph, and using the signal flow graph, some of the complicated problems we can solve easily. Well, so today, before going to next section, let us discuss about one instrument. It is called vector network analyzer. So we have many of them in our lab, and you are supposed to use them for measurement of scattering parameters, S parameters. So this instrument, it can directly measure scattering parameters of any given device. Usually they come with two external ports for measurement of two-port devices, or 4 external ports. Multi-port VN is also available. This is a simplified block diagram of a vector network analyzer. So if you look here carefully, so this is a device under test. It's a two-port device, and these two ports, port 1 and port 2, you can see from outside. These are accessible. So these two ports are connected to two directional coupler. We'll learn later what is directional coupler. So it directs power into two different branches with different ratios. One of them is connected to RF source. So RF source is switchable. So we can direct power from port 1 to port 2, and also in the reverse direction by switching from port 2 to port 1. Now, if you are, let's say, measuring S parameters over a given frequency range, 8 to 12 gigahertz, that you can actually select from the vector network analyzer. Then this RF source sweeps over this 8 to 12 frequency range, 12 gigahertz frequency range. Sorry. And for each and every frequency point, then the corresponding power, it goes through the device. A part is reflected back from port 1, which goes to mixer, and a part is transmitted, which goes to outside and to another set of mixer. Now, S parameters, it's a complex quantity. It has real part and imaginary part. So it can measure both of them. That's why it is called vector network analyzer. We also have scalar network analyzer, where we can measure only the magnitude of S parameters. So in communication systems, I'm not sure you have learned about vector measurement. Let's say some modulating signal is coming, modulated signal is coming. It can be quadrature amplitude modulation or anything else, and you need to measure both its amplitude and as well as phase. So in that case, one mixer is not sufficient. You need at least two equations to find out the amplitude and the phase. So that's why we need two mixers for two observation points. One is called the in-phase channel, another one is called the quadrature phase channel, I channel and Q channel. So same thing to here. And after this, here you can see they are using actually two-stage mixers. So after that, we have the IF stage. So it is basically a super heterodyne receiver inside. And once the IF signal is available, which is in megahertz, then it is digitized, and inside we have a computer. So that takes care of everything. Now, this is a very simplified form of VNA. Actually, inside there are many other components. So one important part when you are going to use any VNA for any measurement, that is calibration. So what is calibration? You see, inside whatever components are used, they are not ideal. So all of them will generate some sort of error. Then what is the overall error of measurement? That we have to first take care. So for that, there are different methods. One of them, which actually you will be using in lab, that is called short, open, load, through. We need actually 4 external known devices. One is short-circuited plane, open circuited plane, load, usually 50 ohm load, and through. That means just a section of a transmission line. Well, so we connect them one by one between port 1 and port 2. And inside the computer, it is already loaded with the program. Then it measures these devices and calculate the error matrix. Okay, so basically these 4 individual devices, they work like reference plane. So with respect to that, we calibrate it. So this procedure is called calibration. So for every measurement, first we do this calibration for accurate result. And once it's done, calibration is loaded from the computer, and then we put the device under test. Well, so vector network analyzer is the instrument which can directly measure complex scattering parameters. Next, excitation of waveguide. So how we really excite a waveguide? So a part we discussed when we discussed resonators, and if you remember that we defined one parameter Q external quality factor. So that is the parameter by which actually we can determine that how loaded the resonator is to external world. It can be external source or external load. So that was for the resonator. Now here, in general, we are going to design some adapters. Let's say with VNA, you have coaxial cables, but you are going to measure a component which is designed in rectangular waveguide technology. So since it is in rectangular waveguide technology, so obviously port 1 for your device, port 2 for your device, it is rectangular waveguide section. Then you can't directly connect a rectangular waveguide to coaxial cable. So for that you need adapter. So in this first example, you can see a coaxial cable is connected to a rectangular waveguide section, and how it is connected, we have a small hole inside, on the broad wall, one of the broad wall, through which this inner conductor is inserted, and through this gap we have coupling. Okay, so inside we want to excite TE10 mode, and inside the coaxial cable we have TEM mode. So these two modes are different, and the inner conductor, it extends deep inside the waveguide. The other end, it is shorted or soldered to the top broad wall. Okay, so this inner conductor, then it is usually represented in the equivalent model. It is represented by a current source I0, which excites this TE10 mode. So in general, then we should learn if inside a rectangular waveguide in this first figure, we may have a current source. It can be electric current or it can be magnetic current, represented by J and M. Now you see, you have to understand what is this J. J, it may have conduction current component JC and also the displacement current component, right? J plus del D del T, JC plus del D del T, sorry. So that is the displacement current component. Now inside waveguide, if I consider, we don't have any conductor, it's air or some dielectric. So it might be the displacement current component, del D del T. Well, so accordingly we need to model, and if we have a source here, then obviously it will radiate power left side and right side. So we might have a forward going wave and one backward coming wave. So if I want power flow in only one direction, so we need to stop one of them. Okay, so I'm coming to that point, how we stop that. Before that, some other transitions. Let's say you have microstrip line, you want to excite a waveguide structure. So what we do, we etch a slot on the broad wall. Now the slot position and its width is important. That determines actually coupling between the microstrip line and the waveguide, or Q external, we can say. If the slot is just at the center of waveguide, so one day we are discussing that it requires a slope of electric field variation. So just at this center for TE10 mode, we don't have any variation. If I put the slot aligned with center, then there won't be any excitation of electric field inside the waveguide.
Sir, you have been muted.
It is from waveguide to waveguide, and in the common ground plane, or in the common metal plane, better to say, in the common metal plane we have a slot. So again, coupling is through this slot, and the slot should be at little offset. It should not be aligned with the center, otherwise slot won't be excited. Now next part, so what happens when, okay, you see one thing, there is one issue. Actually, I can put all of you as attendee, but it will, I have to do it one by one. So I means it takes time. And some of you actually muting me. And again, I have the control actually, I can monitor you. Then I need to change the slide mode to that mode. So you see, if I do that, and if I can catch you, then I'm going to re-register you. So since it will take some time, or it will interrupt to change to that mode again to this mode, that's why I'm not doing. So please remember that. We can monitor you. Sorry. Well, in this first example, this is a metal plate. So since we have a metal plate, electric field will be perpendicular. There can't be any tangential component of electric field. Now we are etching a slot here. So then how this electric field it looks like. So if you look here, then a part of this electric field, it goes through the slot and then again come back to other side. So this one, you can again use that even mode, odd mode concept. If I consider a straight line here, so with respect to that, or on this plane, imaginary plane, just at the middle, we can put a PEC or PMC. Any one of you can unmute and answer.
PMC.
PMC.
Yes. If you yeah, so you remember it then, because electric field is becoming perfectly tangential. So since it is a PMC, then it is called even mode excitation. Even mode excitation, even though just it's a slot. We may have also odd mode excitation that DM Puja did not show. Just maybe I can, in short, I can show it. Okay, let me share better. let us consider a situation when we have a microstrip line on ground plane, and in the ground plane we are etching a slot. So this type of, in this situation we can have actually odd mode, and the electric field electric field, it looks like this. So if I zoom in this metal plane, it looks like this. So in this case, if I put imaginary plane just at the middle, you can see electric field is becoming perpendicular. So then it is a PEC. So this is odd mode excitation of any slot. So in conclusion, then we can have odd mode excitation of slot. We can also have even mode excitation of slot. Okay, so in DM Pojar's book, he has shown just one of them, is even mode excitation of slot. Now for even mode excitation of slot, in fact, means how we model it. We are not going to beyond this point actually. We are not going to model it. So just the physics, how we can do it, the mathematical part, how we can start it by simplifying it. Let us consider a continuous metal plane, and on top and below we have a dipole, electric dipole. So it can be due to polarization, electric polarization. So now if you look at the electric field component, because of this dipole, then it looks like this left hand figure. And now we are interested inside the waveguide. So waveguide is this region, right? So we are interested in this region. Then mathematics, we can start considering a continuous metal wall without any slot, but as if it is having an equivalent electric polarization current here, PE. Similarly for the magnetic field. For magnetic field, it is tangential magnetic field. Now, if I etch a slot on this metal plane, so we are showing cross-sectional view, then a part of magnetic field, you see it bends through the slot, and that's how we have coupling. Here, in this case, we can represent it by a magnetic polarization current, which is parallel to the conductor wall. Well, so this is the first step of mathematics. Then after this, actually, we start calculation. So it is a simplified representation of the actual problem.
Sir, but why does the field bend that way?
Because of this slot. So it has a path, it is not a continuous metal. So it has a path, then it utilizes that path. So even for a microstrip line, if you take a conductor very near to microstrip line, so you are going to perturb the field, right? So field will change because of your conductor. So similarly here, instead of continuous metal, I am etching a slot. So I am going to perturb the field configuration, and this field then follows this slot path. So it is like, let's say you have a pipe and water flowing through that pipe. Now you are making a hole. Then what will happen? Why water will come out? So very much similar to that. But here everything in terms of electric field and magnetic field. Well, so derivation part we are not doing. Directly we are taking some examples. So let me, since this one is one of the most used structure, this adapter we also have in lab. So let us discuss on it. So this is a coaxial cable to rectangular waveguide adapter. Now, when we design any adapter, then two things are important. You can note it down. One thing is mode matching, And the second thing is impedance matching. So what is mode matching? You already know that for one mode, if I look at electric or magnetic field component, if that is perpendicular to the second mode, then there is no coupling between these two modes. One example we discussed. Okay, let me share later. So we are discussing about mode matching. What is that? If you have a square waveguide, inside we may have TE10 mode. We can also have TE01 mode. But if you look at the electric field components, they are orthogonal to each other. Corresponding magnetic fields that will create loop encircling the electric field component, and that lies in a plane which are again perpendicular for these two modes. So in fact, we can use a square waveguide and excite it in both TE10 and 01 mode, and there won't be any coupling between these two modes. These two modes can propagate simultaneously. So we can actually effectively increase the bandwidth by a factor of 2. Two signal we can simply send by using these two modes, and there won't be any coupling or crosstalk between these two. So you have to excite it properly, and you have to connect these two signals separately. Anyway, now let's say I want to design a microstrip line to waveguide transition. So for waveguide TE10 mode, you know that electric field is perpendicular. And what about microstrip line? Again, we have electric field in this direction, right? So now from this electric field orientation, you can actually say how I should place this microstrip line inside the waveguide. So this is the strip, microstrip line. You see, then I should have electric field component as much as possible in the same direction. So then the best way from this field matching or mode matching point of view, I have to align the ground of microstrip line here and the top plane here. Then we have the electric field in the same direction. So for microstrip line, let me represent it by black line, and for rectangular waveguide, TE10. But this is not enough. So this number 1, this is we call mode matching or field matching. But this is not enough. Microstrip line, let's say characteristics impedance is given 50 ohm. For waveguide, we can't define characteristics impedance. But what is our target for any adapter? For any adapter, we want that maximum power should be transferred to waveguide, and reflection should be as small as possible. Ideally, it should be zero. So we call this condition impedance matching. And sometimes we use different shape of transition for impedance matching. Sometimes we need additional matching circuit for it. Okay. Now let me discuss about that coax to rectangular waveguide transition. That is one of the most used structure, most used adapter because with the measurement instrument like spectrum analyzer, vector network analyzer, then RF source, all comes with coaxial cables. And if you want to measure rectangular waveguide, you need coax to rectangular waveguide adapter. Well, so again, let me start from cross-sectional diagram. So this is the rectangular waveguide, and now where I should put the coaxial cable. If I want to excite TE10 mode, I know that TE10 mode, for TE10 mode, it is electric field is maximum on the central plane. So what we do for coaxial cable, we put it at the center, and the inner conductor, it goes up and touches the top metal wall. Okay, so we put it intentionally at the center so that we can have maximum coupling. Now for coax, if you look inside, so electric field inner conductor to outer conductor, it is perpendicular. Then how? It happens because of the current flowing through it, the inner conductor. So if we have a current component, then this current component, it will form loops, right? On this plane, perpendicular. And you now consider for TE10 mode, okay, so my drawing is not good. So this loop, if it is X, this is Y, then this loop, they are in ZX plane. Now for TE10 mode, magnetic field, that is also in ZX plane. So then in this case, the coupling, it is through magnetic field from inner conductor to TE10 mode. Okay, this is the cross-sectional view. Now, as I discussed, that when we put a source inside any guiding structure, so it will excite a forward going wave, one backward coming wave. So how do we take care of that? So what we do, now I am drawing the side view. So wave is propagating in this direction, Z direction. I am drawing the side view. So coaxial cable is inserted here. Now here we put a short circuit, it called back short circuit. And intentionally, this separation, it is taken lambda g by 4. So that any wave, it's coming here, it is reflected back from the short circuit. And for voltage wave, it is in out of phase, current wave in phase. But for this direction, we don't have uninterrupted power flow. Now from top view, if you look here, so this was side view. Now I am drawing the top view. Z is the wave propagation direction. Here you put the back shot and you can just see the inner conductor. Okay, so here what happened, since we are using TEM mode to TE10 mode transition, then impedance matching becomes difficult. So a simple coax cable, and if I just change its position for impedance matching, or if I use some tapering, it won't work. Then we need to introduce some matching circuit. So here usually what we do, we put two metal via. These are metal via which starts from top wall and connected to bottommost wall. So in the cross-sectional plane, then how it looks, this metal via, it is from top to bottom, top to bottom. So this is basically metal wire inserted inside the waveguide, and that provides shunt inductance. So we have to learn then how we conclude the equivalent shunt inductance, capacitance, series inductance, series capacitance, just from this perturbation. So these are metal via inserted for matching. This is metal via for matching, impedance matching. Okay, so this is the coax to rectangular waveguide transition. Now, let's go back to slide. Well, as I was discussing, you look here, this is actually optimized, designed by one of my students. And look at these parameters of this adapter, scattering parameters. It's not that great. In fact, for just a coaxial to rectangular waveguide without matching, it will be very narrow band. So here he tried to design one impedance matching network by using those metal vias so that it can cover at least X band 8 to 12 gigahertz with minus 10 dB of reflection. Okay, so this is just one example. Now, what about coax to microstrip line? Coax to microstrip line, it's almost similar. Here, if you look at this first picture, you can see again it is inserted from below the ground plane, and we have that field coupling. It's through aperture in the ground plane, and we can change here the aperture dimension that will determine the input impedance actually. But we have a better technique than this, which is automatically wideband. So instead of inserting it from below this ground plane, what we do is turn the coaxial cable by 90 degrees so that it becomes horizontal with respect to microstrip line, and then it looks like this. So this left side, I am showing the coaxial cable. The right side, it is the microstrip line, and it's a cross-sectional view. So this middle one, you can see this is the inner conductor of coaxial cable. It is little extended outside, and we solder it to top microstrip line. And this green part, this is the dielectric of the coaxial cable. Now it is automatically wideband. Why? First of all, if you look at, for the field matching part, if you look at the electric field configuration, inside coaxial cable we have inner conductor to outer conductor field direction, right? Inner conductor to outer conductor in this direction. It can be from below to top direction or just the opposite. Okay. Now inside the microstrip line, we have field direction in the same direction. Here also we have perpendicular field component, so it is automatically matched. And I am not using this upper half, otherwise for the upper half direction is in opposite direction. So if I use upper half, then they are actually cancelling out. So intentionally I am not using the upper half, only the lower half is connected to microstrip line. Okay, so field matching part is automatically done. Left side TEM, right side also TEM, and the electric field they are in same direction. Now, what about impedance matching? Coaxial cable, if it is 50 ohm, microstrip line, if that is also 50 ohm, then automatically impedance matching is also done. So that's why you see SMA connectors, and there are so many connectors we discussed when we read about coaxial cables. And most of them, if you notice, they are called end launcher, and we connect them just like this. Inner conductor is soldered to the microstrip line, outer conductor is soldered to ground part, and they are automatically matched. So if I compare the result with this one, coax to waveguide adapter, so it can start from 0.1 gigahertz to 18 gigahertz with at least minus 20 dB of S11. So you can compare this value. 0.1 gigahertz to 18 gigahertz. This whole bandwidth, just one adapter without any matching network, it can cover. And S11 is much below, let's say below minus 20 dB. And it happens because of this field matching and impedance matching. It is automatically satisfied. Well, so in practice, sometimes what happens, let's say you are going to now measure your waveguide based or microstrip line based component by using vector network analyzer. But this adapter, it is not ideal. Coax to microstrip line or coax to waveguide, this adapter is not ideal. So it will give you some change in magnitude and change in phase, but you are not interested in it. You are interested to measure test parameter of your device. Then what we need to do? We need to nullify their effect. So if you want to nullify their effect, you have to first know what is the S parameters of this adapter itself. Okay. So if you know that, then actually we can do error calculation. And we have a separate calibration method. It is called TRL calibration. Maybe while doing practical classes, we'll discuss in detail. Through reflect line. So where actually we can take care of these adapters and we nullify their effect in the calibration process itself. Okay. So here just for some idea, and you should remember this point, that this adapter can change the expected result of your device, because it also has some S parameters. It is now looking like a two-port network, and this is one arbitrary equivalent circuit, so it can change from adapter to adapter. Well, so we use this term equivalent circuit so many times. So what is that actually, and why we need them? And the third point, that how to find an equivalent circuit. First of all, if we first learn Ohm's law and Kirchhoff's law, current law and voltage law. So it is easier for us to think in terms of current and voltage rather than electric field and magnetic field. So if you look at the Maxwell's equation, the equation itself looks very simple, but when you go to think about electric field, magnetic field distribution in space and time, then it becomes complicated. Sometimes simply we can't think. So then it is a tradition. That's why if you just give the terminal behavior and try to represent it in terms of L and C, then it becomes easier for us to understand it. So this equivalent circuit just for understanding the problem. So actually the equivalent circuit may not have sometimes any relationship with what is actually happening inside the structure. Then how we design the equivalent circuit or extract the equivalent circuit? This is just by looking at the terminal behavior. We don't, sometimes we don't consider actually what is happening inside the structure. So look at the terminal behavior. Terminal behavior means S parameters or Y, Z or ABCD parameters, which we measure at the port. Well, then the third point, how to obtain the equivalent circuit. Here we have a problem. For some simple cases, you can directly do it. For some complicated cases, the circuit is so complicated, it's really difficult to obtain an equivalent circuit. Okay, and sometimes it is a research topic actually for some PhD students, because particularly for active devices, what should be the equivalent circuit at microwave frequencies? For that, even the equivalent circuit will change with biasing voltage because it's nonlinear. So it is also a research topic for some PhD students. Well, for now, we consider some simple cases. And before that, let me give you some conceptual idea. Now, you have full wave simulators. So you can plot scattering parameters. You can obtain it from full wave simulation. And from the scattering parameters, you can then predict at the port, is it looking like a series inductor or shunt inductor, series capacitor or shunt capacitor. That is the for simplest cases. Sometimes it can be a resonator if the input impedance crosses 0, right? So here one simple example, we have a section of transmission line. Intentionally, I took 90° at 10 gigahertz. Now I am plotting angle of S21 measured at ports. So if I plot angle of S21 at 10 gigahertz, it should be minus 90°. So look here, this black line, it is for this 90° transmission line, and it is 90°, minus 90° at 10 gigahertz. And equivalent electrical length will change with frequency, that you know. Theta is equal to beta into L, and beta is 2 pi by lambda g. Lambda g is changing, equivalent theta will change. Well, now in the same line, in the first case, I am putting intentionally one inductor in series. What is the value? 1 nanohenry. This 45° line still remains. So now minus 90 with some additional value we are expecting for angle of S21. Now for inductor, you know, current leads. For capacitor, voltage leads the current. Then here, what we expect, that angle of S21, which is related to voltage amplitude, it will be down, it will lag compared to this simple transmission line case. So then for this one, minus 90 plus some additional term. So here you can see the value depends on the inductance. Okay, so we have some higher value. So then you see, we can compare a device with some equivalent length of microstrip line or transmission line. Then we compare that angle of S21 is decreasing or increasing. So based on that, then we can comment there is a series inductor or series capacitor. Capacitor, you see it's going up because voltage leads here. Okay, so it's going up. So this is simple cases. You can do it for shunt inductor and shunt capacitor also. Now, if the angle crosses 0, then obviously we have both inductor and capacitor. Then it is a series resonator or parallel resonator. It is a second thing, series resonator in series or in shunt. The parallel resonator, it is in series or in shunt, right? So that you have to find out, and for that you need also magnitude of S21. For example, if I put one series resonator in place of inductor, series resonator in series. So series resonator, you know, at resonant frequency for ideal series resonator, impedance is 0. So basically it has no effect at the resonant frequency, series resistance becoming 0. So then magnitude of S21, ideally it should be in dB scale 0 dB, right? Now if I go left or go right, then it will decrease. So if that is the case, then we can comment most probably it can be either a series resonator in series, or same thing also happen a parallel resonator in shunt, because for parallel resonator at resonant frequency impedance is infinite, so it has also no effect. Then it is series resonator in series or a parallel resonator in shunt. How do we comment? So magnitude is not enough. Now we have to look at the phase. For series resonator, you know that below resonant frequency, it behaves like a capacitor, na? And above resonant frequency, it is like inductor. For parallel resonator, it's just the opposite. So if you then look at both magnitude and phase, you can determine actually what is the exact equivalence. Well, it looks very simple, but here you have just two unknowns. And fortunately, we have two observation points, one for magnitude, one for the phase of S21. But instead of 1 0 crossing, if you have more than one, or if it looks different than this, then it becomes complicated. There are many combinations possible, and it's not just two components, there can be many components. Okay, just to give you some idea, when this problem can be complicated. Well, so this step actually I summarized here. You can do it in terms of ABCD parameters also. And some of the popular structure here and there equivalent circuit I represented. Again, simple one. So here we have a rectangular waveguide, and what we are doing, we are changing the width of rectangular waveguide by putting a metal plate. In the first example, this one, left side a metal plate, right side a metal plate. So it becomes basically a narrow. It's a diaphragm. It's a thin metal plate, not that along the waveguide. It's a thin metal plate, and it is represented by shunt inductance. So usually it's like a thumb rule. If the perturbation, whatever you are putting inside the component, because of that, if magnetic field changes most, then most probably it will be inductor. Now it is series or in shunt. Look at the phase response. If you disturb the electric field most, then it will be a capacitor. Okay. So this is an asymmetrical inductive diaphragm. Here, between now top and bottom, it is capacitive. Here, asymmetrical capacitive diaphragm. Equivalent circuit is shunt capacitor. How we say that? Again, you have to go back there. Okay. Next. Now we are putting all over it. You see, left, right, side walls, top, bottom, broad walls. Then it behaves like a resonant iris, and its equivalent circuit is a parallel resonator in shunt. So we can have a circular resonant iris. We can also have a rectangular resonant iris. Okay, so how we obtain that, we already discussed. Here, change in height, it is like a impedance step. So it will give you shunt capacitance. Change in width, it will give you shunt inductance. So you see, when we are doing along width, it is mostly disturbing your magnetic field loops. So always that's why it is represented by inductors. Now for microstrip line case, some of them you already know. The first example is section of microstrip line in distributed form. For lossless case, we represent by LC section, that you know already. Distributed form of any transmission line. Well, now we are putting open stub. Again, we discussed this. If the open stub length is less than lambda g by 4, then it is input impedance is capacitive. So we represent it by a shunt capacitor, and it is less than lambda g by 4. But now other end is shorted, then input impedance is inductive, and we have an inductor in between these two. If in the second case length is more than lambda g by 4, then it would become capacitive, obviously. So we can have shunt capacitor and shunt inductor. What about the series component? We also may have series inductor and series capacitor for microstrip line. If I use a narrow section of microstrip line, we can have series inductance. So actually, we use this configuration and this configuration together to design low pass filter. One type of low pass filter is there. It is called high-low low-pass filter. In this last example, we put simply a slot, a gap in the top microstrip line. And this gap is represented by a series capacitor. Some people use a more accurate model. They represent it by a pi network for both inductor, this one. Well, we are considering the simplest scenario. So it can be represented by a series capacitor. Well, till this point, let us take a few questions. If you have any questions, so please switch on your microphone and ask me.
Sir, in the previous two slides, slide 46. So the thing is that so that is the cross section of a rectangular waveguide, right?
Yes. Cross section, yes.
It
You
has
see,
a transmission line.
No, you are confused. Then what we discussed in last 1 week? It is not a transmission line. We are considering only the terminal behavior at the port.
Okay,
we are considering network
that is
analysis.
Equivalent circuit.
Exactly, equivalent circuit. I wrote it here, also said this point. So I said now, when sometimes we are not simply interested what is happening inside the structure. That is the part of microwave engineer or RF engineer. Now, when you are a system engineer, you are interested what is happening at the port. Let's say one RF amplifier. So RF amplifier, one microwave engineer will design. But as a system engineer, you will specify my requirement is this much of gain over this frequency. So you design it. Then you will be measuring these parameters at the port.
So this is the equivalent two-port network.
Yes, exactly. At the port only. So if you compare the S parameter response of this one and this one, at the port it looks similar. That's all. Understood?
Yes, sir.
Sir?
Yes.
Sir, in the same slide, means if we are using the symmetrical inductive diaphragm, means we are decreasing the width. So wouldn't that change the dominant mode frequencies and all?
Yeah, you are right. So that happens if I put a continuous perturbation. So that means, let's say I'm showing the top view. Okay, so this is your waveguide 1 and you are adding waveguide 2 here. So waveguide 2, it has a different cutoff frequency, right? And that will happen for this one. Now let's say first waveguide has a cutoff frequency of 6.5. Second waveguide has a cutoff frequency of 9, and you are sending 10 gigahertz signal. Then what will happen? It will pass through both of them, right? And at the junction, you have the effect of this junction is this shunt inductance. Well, also, this is the top view. I am considering a different situation now. Actually, what I represented here, it's a small metal plate inserted here. Okay, and we have a gap. So we don't have even any cutoff frequency or anything like that, because it is a simply perturbation. So let's say the thickness of this metal part is 0.5 millimeter. So it is a section of waveguide then of length 0.5 millimeter. So it is basically nothing. We can't model it by a guiding structure. Better we model it by its equivalent model. Because if you look at the field configuration, you can't identify TE10 mode here. We have Evanson mode, other higher order modes. So it will disturb the field configuration actually. You can do it. You have full wave simulator and try to understand it. So that will actually build up your concept. I have shown here the top view in this example. Wave is propagating in this direction. Is it fine,
Sir?
or you need some?
Yes, sir. Sir, and also when you were mentioning the concept of using the adapter for coaxial cable rectangular waveguide,
Mhm.
and if the rectangular waveguide was excited in TE10 mode, and
Mm.
then in the middle the electric field would be maximum, so the coaxial field is a short circuit, right? Means basically it's a metal wire. So wouldn't
No,
that
no,
change?
no, 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 no. You are confused with circuit theory. You see, single conductor have you used anywhere at micro frequencies?
No, sir.
Now, if I have a single conductor, the situation is completely different. For a small part, you can think like your low frequency case, 50 hertz case. Okay. So since this length is very small, so we are considering that as if a current carrying wire. And if you have a current carrying wire, so surrounding the current carrying wire, you have magnetic fields, no?
Sir.
So through that field, actually, we are exciting this magnetic field component of TE10 mode. Now, of course, this part is shorted, but this short circuit is not like the short circuit concept we use for microstrip line, because here it is TE10 mode. So how do you call? Means just by one side short. For microstrip line, there is a defined ground. Anything you connect to ground, you call it shorted. But for waveguide, can you call top plane or bottom plane as ground?
No, sir.
So that's why you should not use that term. It is shorted. Better you use the term it is soldered or connected,
Okay, sir.
not short circuited. Basically, shorted word still you can use, but it is not short circuit. You have to consider everything in terms of wave, electromagnetic wave. Yes, it's good that you are thinking on it. Any other question? Okay, then I can stop here. Thank you all. If you, okay, this Saturday we will be having a tutorial class from 10:30. If you have any other question, you can also type. For now, let us stop this session.